Okay, so you've completed this analysis of a picture that is a little bit puzzling, and we noticed that this fence is split in half. And the reason that this fence is split, it has nothing to do with the construction. It has everything to do with earthquake activity. And so I'm going to draw in right here. This is where the fault line, sorry for that little up there, but the fault line would actually be running not parallel to the fence, but perpendicular at a right angle to that fence. And because there was a shift on the fault line, that's the recipe for making an earthquake, we see this split fence. Now, another picture from the same area, which is called Point Reyes, I'll show you on the map here in a moment, is this. And you can see on this picture, someone has already drawn in the fault line. When my colleague, Mrs. Engineer, saw this, she said, "Oh my gosh, stupid farmer, who builds a fence like that?" No one. That's really stupid earthquake. So today you're going to be learning more about how this giant crack in Earth's crust called the San Andreas fault line, how it actually operates with earthquake activity. So right here on this map, you'll notice near San Francisco, north of it, there's Point Reyes. So this is where that picture of the split fence during an earthquake was taken. Now, one thing you should know is this is actually a bit of a simplification. This is the main crack in the crust, but if we could see the entire fault system, you would see smaller fault lines branching off almost like branches on a tree. So anyway, what I have today for you is how in the past, before global positioning satellites, scientists actually measured movement on the fault line. They measured it just like that picture through broken fence lines. And so I have for you today 7 of these models of fence lines. So this would be like the lithosphere, right? Also a tectonic plate. That's another name for it. And then here, this would just be like the soil where the fence was built. And during an earthquake, there's shifting. Let me show you again. There's shifting on those. The soil's sliding. There's shifting on those fault lines. So what we're going to be doing today is you're going to be doing is recording the amount of displacement. Now, displacement is just fancy for movement. And so what we're pretending is that these 7 models are different locations. See those white dots? All along the San Andreas fault line. Okay, here we go. So this is the first one. And so you've seen me already move it. Now sometimes people make an error and they want to measure across. That's the length of the fence. That's not the movement on the fault line. So I come right here and get ready to type. This one is 4 centimeters. So our first one is 4. And that maybe, we're just pretending maybe that was Fraser Park, and then maybe this is similar north of it. This displacement, here we go. This one is only 3 centimeters. So we have 4 centimeters, then 3. Now this is representing movement on a different location of the fault line. So maybe this is like Parkfield. Here we go. Whoa. Okay, get ready. This is much bigger than the other 2, 8 centimeters of movement. Okay, now let's say we're moving north and maybe Hollister. That's not just a brand of clothing, that's actually a location. So this fence got split during an earthquake, but the movement this time only 2 centimeters. Okay, so we have 3 more locations to go. Again, representing different spots along the San Andreas fault line. This is the 5th spot. And this is not quite our largest. Let's go 6.5, 6.5, 6.5. Okay, and then 2 more locations. This one is just an even 6 centimeters. Okay, and then finally, our 7th and final location, much smaller displacement, 3.5, 3.5. So now that you have all those, you're going to add them up, divide by 7, and get the average.